with the differences between hybrid and native. And having one address for L2 management and a separate address for L3 management became absolute ick. Our lower level operations staff would get lost, couldn't find their way through the box. It's got some value in what it offers to you, but for us, it just didn't work. We also did a lot of router to switch consolidation and then trunked it over to a switch where our co-location room was to then fan out to the customers. Again, the router port always looks like it's up, so the operations staff thinks there can't be a problem. And it just complicated the troubleshooting for our NOC staff. So where the opportunity presents, we continue to get rid of this anywhere and everywhere possible. So on the topic of hardware complexity, once you grow beyond a single router, you'll likely find you need to become an expert in what you've got. Plan for this. We made the mistake of throwing 7507s into our network before we really knew the typical failure modes of VIP2s. Because they're not ECC memory, they like to crash on you. Becoming very familiar with troubleshooting charts made our life real easy. Maybe not necessarily recovering from the crash, but at least beating up on vendors to get replacement memory shipped out where appropriate. Boy, did we have a lot of lessons to learn about GSR engines. Boy, was it a surprise to find out that engine 1 can't do priority queuing. And then, obviously, line cards. And a quick disclaimer, I apologize, we are a Cisco-only shop. We're small enough and just don't have the development budget to do much experimentation. We kind of live on the, not at the just-in-time, but the we needed it 2 weeks ago method. So design your network. As you're starting from a small network and moving your way up, one box per pop probably doesn't work. When I came on board, everything was Riverstone. Flow-based forwarding just wasn't fun. Port scans were terrible on us. We tried doing distributed forwarding, but found that the older cards we had would only handle 100,000 routes, and they didn't know what to do with the prefixes that didn't fit in. Be consistent where you can, but don't make everything fit a mold. We did way too much of trying to do everything with the same size router, and we're getting better now at picking the right sized box for what we're doing. Core network design. We started off with 2 core routers per pop, and that's kind of what was worked well for us, but the architecture has shifted a little bit. You'll need more core routers when you've outgrown this presentation. This is for small operators, you know, whatever size you feel is small, but it works for us. So by going to a routed model, think a /30 or a /31 per link. If you're doing 2 core layer 2 switches, we ran into a lot of pitfalls on this. So referring to the 2 core L2 switches, here's an idea. We found that the capacity scaling was just a challenge. If you had some of these links as gigabit and some of these links as fast Ethernet, you'd have queuing issues in the switch. Routers wouldn't know where to send traffic intelligently. You also have strange failure modes as links go down, especially 2 random links, one on one switch, one on another. You just don't know where your transit traffic's going to end up. So as we move to the 2 core routers per pop, so yeah, convergence issues and troubleshooting, we ended up with 2 core routers that connect to each other. We try wherever possible to do 2 links between the 2 core routers, preferably card independent. Murphy lives in our walls, and we try to do what we can to beat him back. Downstream connectivity on what we termed distribution routers. Each of those distribution routers connects to both core routers and nothing else in the POP directly. Our upstream connectivity, where we were getting connectivity, is on what we termed edge routers. Everybody's got their own vocabulary, but going forward, this is our reference. Again, each edge router connects to both core routers and nothing else in the POP. And then the POP-to-POP links, your WAN links per se, connected on our core routers. So there's a diagram of the connectivity. Tried to be a lazy guy drawing the link between the 2 core routers, but you can see how it goes. Each of the links you see would be a /30 or /31, scaled a lot better for us. But in the beginning, we made the mistake of trying to do all of our core routing and all of our upstream connectivity on our core routers. Got us going, but we ran into an interesting pitfall in the iOS BGP path selection algorithm, where Rule 9 says prefer your external BGP path over your internal BGP path if it's not already selected earlier, which meant that our inter-pop traffic left by the logically closest link, unless another link was drastically better. So here's a diagram of our old method. If traffic in City 2 was heading perhaps for the right side cloud, it would get onto Core 1, and Core 1 would say, I'm going to prefer an external path, and I'm going to send it out to this direction. It made a lot of our traffic tuning an interesting challenge. Likewise from City 3 on the right. Trying to keep control of our provider bandwidth utilization was a game. Try an iteration, see what it did for us. Try another iteration, try and get closer. So we solved it by bringing in edge routers, which were theoretically equidistant from the core router. So traffic from City 2 would come into Core 1, and it now has two equidistant external options, well, technically internal options, before going out to the cloud. And that allowed Core 1 to pick whichever exit path made more sense rather than being drastically glued to the external first. As far as IGP design goes, we started with OSPF because we were working on multi-vendor, switched to ISIS on the premise that it would be more secure because we weren't accepting CLNS frames externally or from our customers, on a premise that it would be operationally safer because we do MPLS VPNs. We would potentially have customers wanting to do OSPF routing with us. So by having our operations staff doing router OSPF commands all the time, they couldn't accidentally stumble into router OSPF 1 and foobar our core routing. But we found that some hardware out there doesn't have ISIS support, or it's not where we want it to be. So we're starting to plan going back to OSPF. Either way, our lesson was you want the versatility. When you get into a scenario where you want MPLS traffic engineering, for example, you're going to want OSPF or ISIS. Pick what suits for you. EIGRP wouldn't do it for us. Keep your IGP lean. It's been in a lot of other presentations, but it's made a lot of sense for us as well. Keep everything else in BGP for the administrative control and the scaling. So credit to VJ Gill and the ATDN team. We copied their model from a previous NANOG presentation and found tremendous simplicity in it as we were rolling it out. We start with a table of metrics by pipe size and then add a modifier depending on where in the network that pipe physically exists. So admittedly, we took the long view. We have nothing larger than gigabit Ethernet, but we plan for all the way up of what's current or reasonably forecast. This is the base metric table we use. From that, we modify it so that links between core routers are metric of 1, regardless of their pipe size. A backup core link might be higher, it might match the table, but we tend to have equal size core-to-core links. Links from the core to the edge or core to distribution are based on the table plus a value of 500. WAN links are the value in the table plus 30. And there have been some minor tweaks for BGP tuning purposes. We also use 10,000 plus the native value to indicate a link that's being worked on. It shifts traffic off the link for us automatically. Link metric of 20,000 plus the table where we are bringing in a new link or taking one out. So there's a little bit of automatic documentation of what's the operational status of the link by looking at the metric. So by using this metric design, a failure of the links between the two core routers and the POP prevents the transit traffic from going through an intra-POP edge router or through an intra-POP distribution router. Traffic will prefer to flow around the WAN, and reason for that is the links from disk to core might not be sized for the transitory traffic on top of it. As an example, not exactly to scale, but somewhat representing what's going on, our 2 core routers have a metric of 1. All the other non-core routers in the POP are a metric of perhaps 507. A lot of our stuff was fast Ethernet. Links from city to city are in the 30s, and then in another city, the links from core to the outer edge are in the 500s. So a loss of this link in the center prevents traffic from going through here. It would much rather find a path around the WAN where it could presumably go through roughly 14 cities before it would find that that route would be less preferable than going through the local core or the local disk or local edge. Some pitfalls of that metric structure. We had links to 2914 in Dallas and in Houston. The next rule in BGP path selection for iOS is prefer the route that can be reached to the closest IGP neighbor. So IGP metrics do factor in here, and we got bit. All of our connectivity is in Dallas and Houston. Our San Antonio POP is connected to Dallas and connected to Houston. San Antonio Core 1 went to Dallas, and based on its BGP table, it preferred certain prefixes through 2914 in Dallas. Core 2 was connected to Houston. It preferred 2914 through Houston. And we had some interesting intercity traffic patterns that we finally tracked down to be because of IGP metric. We tweaked some metrics between the Houston core routers and Houston Edge 1, where our 2914 link was. All of our San Antonio distribution routers had BGP multipath enabled and went boom, running out of RAM on the VIP and the RSP simultaneously. Compounding the wonderful excitement of that event was the fact that our headquarters office and my desk are connected by T1s off of one of those distribution routers. So not only did the 4 routers run out of RAM, I lost my ability to look into the network and see what was going on. Oops. So figure out where you really need BGP multipath and plan that in your hardware purchases as well. Moving on to BGP design, it's made to scale, so use it. We carry all of our customer link subnets and our customer LAN subnets and obviously our external routes in it. It's got great filtering tools. I highly recommend you use them. We filter at every point of ingress and every route injection point. In doing so, we imply an internal community allowing us to interpret that route rapidly from any other router in the network. Some of the scaling pitfalls that didn't work for us: we were a confederation shop. I was the one who made the decisions. It looked good to us in the very beginning. It was a little easier to get documentation on it for the stuff we had. But one sub-AS per POP meant that each router was its own sub-AS. Convergence was painful because the routers would end up exchanging the entire table, not just best routes. And the sub-AS path tried to be an IGP, and it'd be much easier to do it on the scale of hundreds of routes rather than hundreds of thousands of routes. So we removed confederations and then deployed route reflectors. And going back to the ATDN transition and taking a long view on our project, we disabled client-to-client reflection, which my understanding is it helps minimize net oscillations and related funnies, and it allows a little bit better scaling as you're doing multipath to various clients or providers. So we just redistribute connected routes into BGP. We exclude the interfaces that are already in the IGP, and one of the oopses that we ran into was the route map handling this was, and in many cases still is, written to deny based on interface name. If you end up with a failed VIP, a failed line card, whatever, that interface no longer exists. If you happen to reboot the router at the same time or something like that during a card upgrade, what have you, the router will recalculate the route map And that line, which previously denied only one interface, now denies all prefixes. So we are shifting to excluding our IGP interfaces based on prefix list. Fun little challenge to troubleshoot. I was home on a Christmas vacation and didn't make any sense, but dig into it and oops, yep, that line's not doing what we want it to. Likewise, we redistribute static routes into BGP and allows us to do all of our customer configurations on the distribution router where the customer is connected and not have to touch anything anywhere else. What you'll never find in the various BGP textbooks is that transit costs money. Peering is usually no or low cost. It's debatable. Customers usually result in revenue. So from a design perspective, what the books don't tell you is many networks treat their prefixes appropriate to dollars. Prefer to send traffic to a customer, if that's where the prefix lives, rather than through peering or transit. So the often used hammer to do that is local preference. So as a sample local preference design, ours is a little bit skewed from this, but it's a good basis and it's what we're shifting back to. Customer local preference of 400, peer local preference of 300, transit of 200, and a backup route would be a local preference of 50. Key here being with the default local preference being 100, a forgotten or flawed route map will result in routes that aren't used. If you forget the route map and learn prefixes from your customer, they'll come at local preference of 100. You'll still send the traffic out through your transit or better connections, and customers say, why is my traffic not coming over our link? It helps to force the troubleshooting and the observation of the problem. And likewise, if you bring up a transit connection, you're not going to swamp your routes the wrong way because of an incorrect route map. So our customer filtering plan. Filter once on ingress, apply that internal community, and we do so aggressively. Because we're a small enough shop, we filter on a combination of prefix and AS path in such a way that the customer can prepend freely using the ASs allowed on that path. We also allow our customers to shorten the AS path as desired if there are multiple ASs on the path. Let's say our customer has a downstream customer with a /24. Downstream customer's router blows up, they replace it with a small box that they don't want to run or can't run BGP. That customer of ours might get asked to announce the prefix. The AS path will most likely have changed. In doing so, we allow that prefix to make it out the door and allow that customer to continue using the net. We do not allow our customers to change AS path without prior contact and configuration changes. We don't allow them to lengthen it other than prepends. We tell them about the filtering rules and lots more at turnup. We have a 4-page document that covers a lot of our BGP stuff in that they get on turnup. So in doing the community on each prefix, it's a coded community, covers the POP of origin of receipt or ingress, indicates a requested egress handling that's sometimes overridden but sometimes not, and a type of the route, whether it's a customer route, our own route, or an external. And then try to use this tag intelligently. We use the POP of origin to adjust MED automatically for us on egress to our providers, allows simple geo-routing, and has done drastic things for our WAN costs and size of pipe needed. Our design, left side is our AS number. The right side is 5 characters. First indicates route type. Second and third indicate POP of origin. Admittedly, we only have 5 POPs, but if we did double, we'd be out of characters, so we went for the long view. D is our desired tuning. 0 is as I've managed to tune it over time to keep our links balanced as desired. 1 is basically wide open or whatever our providers tend to tune at. 2 requests backup handling, less traffic on it, and 7 would be for maintenance, indicating this route's only if I have no other way to handle it. And then E is our trigger for aggregate and hot potato routing or POP specific and cold potato. After that, for our customers to have some control, we developed a set of communities that we sometimes use and our customers are always eligible to use for tuning within our network, used to set local preference and adjust how their routes compare on that previous chart to allow them to balance with our transits and peers or come in below it. And if they should want to have the option of both customer level local preference and customer backup that's still essentially better than transit, we allow them to do so by using MED. In the case of customers that only have a single connection to us, we have a simpler inbound route map that squashes MED to minimize any troubleshooting surprises from it. So for basic versions of local pref, they'd use 11457:400, for example. If they wish to null route a prefix, the right side would be 0. So in our customer inbound route map, 5 basic categories in the route map. The number of entries in the route map grows based on how many AS paths they might be sending us routes. First option for us is to accept a null routed aggregate route. We will accept it, we will null route it, and we will propagate it to our providers. Because it's one of their aggregates, there could be a lot of valuable tools, which we'll show on a chart coming up, why they might want their aggregate route null routed. Second in the route map is to accept null routed specific routes from them. Anything matching their prefix length all the way out to /32 is accepted, tagged no export, null routed, and shared within our network. This allows them to, based on the third step, accept their aggregate and propagate it, which is the typical expected behavior. So now using the second and third clause, they could announce us their aggregate and using the second clause, null route any portion of their space. We will also accept a more specific with a specific community, allowing that prefix to be propagated, even though it didn't match our original exact match filters. It's a best effort feature, hopes that our transits filter on less than or equal to 24, but it allows us from a small shop perspective to simplify our support requirements. And if a customer for some reason in an emergency situation needs to announce a more specific for traffic engineering purposes or whatever, they can call us up, we'll tell them the community to use, they can apply that community to their route, it will instantly go out through our filters and allows a technician or myself to circle back in the next 12 hours per se and add the appropriate filter entries and request the specific filter openings on behalf of our providers. We have not gotten large enough to automate that. And the last entry on the prefix list is to accept a specific that does not have the community for propagation. So it would be simply a specific and does not have a community for null routing. And we will accept the route, we will tag it no export, share it within our network. This allows both a anti-spoof filter override, so if by chance they're announcing their aggregate to another provider and not to us, but they do have certain prefixes they want to be able to send out through us, they can create an RPF opening. It also allows them to do a null route override. Let me jump ahead to this chart. So here's a sample of the customer filtering logic. I'm going to highlight the first, second, and last clause there. We will allow null routed aggregates and propagate them. So for example, if the customer is allowed to use 10/8, we'll accept it, we'll null route it, and we'll propagate it. Jumping down to the fifth clause, we'll allow customers to announce a more specific to us and tag it no export. So in this case, the customer might announce 10.20/16. We'll accept it, we'll distribute it internally, and that more specific will actually propagate, and the packets heading for that prefix will come in our upstream edges, travel through our core, down to the distribution router, and head out to the customer. Jumping back to the second clause, we'll accept a null routed more specific and tag it no export, and of course null route it. So the customer could announce 10.20.30/24. We would accept the prefix, distribute it internally, and arrange for null routing. So if we look at the chart on the bottom, 10.0 through 10.19 would get null routed because it's carried under the first block, the 10/8 aggregate. 10.20/16, I'm sorry, 10.20 through 10.20.29 would be routed because it's carried under the fifth block, the 10.20/16 acceptance. 10.20.30/24 gets null routed, carried under the second square. 10.20.31 through the rest of 10.20/16 is routed because of the fifth square. 10.21 through the rest of 10/8 would be null routed because of the initial aggregate /8. Fairly complex, but allows the customers to nail up large aggregates, use small portions of them, and not be subject to massive traffic swings or router implosions in the event of a DOS. Obviously, they could simply announce their aggregate normally and null route a few particular prefixes. This was relatively easy to implement, given the other filtering we were doing, and gives the customer a lot more flexibility and control as desired. So the side impact of this filtering is that we have at least 2 prefix lists per customer. One of those prefix lists is an exact match list per AS path. So if they have a prefix and a customer of theirs is doing BGP with them and does a prefix, we would have 2 exact match lists. There'd be an additional list that's just matching on the aggregate out to /32 for null routing and the temporary specifics discussed earlier. They can optionally inject tuning communities. We have the option of injecting tuning communities as desired. We've got numerous customers that are new to BGP, need help in tuning, can't understand why half their traffic comes through us, even though they've pre-pended it 12 times. We know that they've got to fix local preference externally in order to get that to balance the way they want it. So we will often inject those communities and tell them you've got 30 days to arrange for it yourself. Anytime thereafter, we might remove the community and you'll be on your own. So with that BGP tuning design, we came up with another set of communities that we or our customers can apply to routes for tuning outside the network, including no advertise, the setting of prepends, and the requesting of local preference. So on our edge routers on the outbound path to our providers, we obviously filter out other upstream routes just to double make sure that they're not going to go out that way. We allow routes that are flagged with individual and/or global local preference or prepend requests. And this became rather complex. We were pretty dependent on route map continue to make this work. But our customers can do individual local preference and global prepend configurations or vice versa and layer it as they wish to. We've had a couple of requests for this already. If there are none of those local preference or prepend requests on the route, then we will allow routes that are flagged for internal to our network local preference and map a corresponding local preference, because we found that BGP instability will show up if you've got a if local preference does not equal or go down, relatively speaking, as the route travels outbound. If there are none of those communities present, we process the routes based on the embedded tuning, which was the D character mentioned earlier, and then we set our MED based on the embedded E character and what the pop of origin versus pop of egress is. So for our BGP outbound tuning, we've finally gotten ourselves to a point where we've got parallel connectivity to 3 transit providers. We're not in a good position to peer much yet, so we're reliant on transit. For each of those 3 providers, we've got a link in Dallas and a link in Houston. For those transit providers' address space blocks and their customers, we do cold potato. We presume we're getting med from them, we use it for intelligent routing, and we'll send it through our network to get out to there, through whatever exit point they're suggesting. If it's a prefix that's beyond that radius, we'll send it hot potato. We'll just give it to them and let them take it from there. So reasoning behind that is that in a normal state, assuming that we don't have links or routers down, cold potato routing is only 1 hop longer within our network for us because it's normally 2 hops from distribution through core to edge. It would only be 3 hops from distribution to core to another city's core to an edge. So summarized, we know our network. Because of the presence of a med on those prefixes, we assume that our provider knows their network. But we also take the view that we know our network better than we know their network, because all we're getting is med and we don't know anything about their IGP metrics or whatever. And the assumption is if they're telling us that a particular POP is better, we'll use it. So the assumption is the med learned is likely based on or otherwise derived from IGP distance to the point of aggregate injection. So if it's the transit provider's aggregate prefixes, the med probably points us to whatever core location or POP location they're using to inject the routes. And if it's one of their customers, we presume that the customer has either tuned med or is doing med equivalent across all pipes. We're assuming that the provider has now chosen a best path through their network to the point of best med from the customer, so that the provider's med will lead us to that best exit point. Moving on to traffic engineering. We had some interesting challenges in redundancy planning. We've done some simulations by changing the metric on links, but we've learned that all too often, if we're striving for N+1 redundancy, we've got to kind of back calculate our capacity planning and probably start ordering new capacity at N+2 so that by the time it actually shows up, we're just barely squeaking beyond N+1 and about to run out. And from GI Jane, 2 means 1 and 1 means none. Sometimes with 2 core routers, 2 over 1 means half your capacity is excess. Ugh, but it's what you might have to do. So because we're only a 4-city network with a strange traffic pattern sometimes, MPLS traffic engineering saved our butts. We had, before we got to the parallel providers, we had over 100 megabits traveling across our Dallas to Houston WAN when our overall traffic was only 150 megabits. So in the toughest of times, we had 1 or 2 TE tunnels from each distribution router to each edge router and vice versa. And we ran on very aggressive 15-minute auto bandwidth timers. A lot of RSVP state, but it was enough to get us out of trouble and utilize the non-equal cost links to gain some capacity and retain some redundancy that would otherwise have been quite expensive to engineer directly into the network. And of course, we had some pitfalls. One of our customers was running a news server, and that meant a few large bandwidth flows would get glued to a particular tunnel. And here you just add a couple of tunnels where you know you need them for granularity. Once we started moving into different platforms, ran into some iOS issues. They got in our way, made things get pretty ugly when the hourly reoptimization timers hit. So we cleaned out all the dist to edge and edge to dist tunnels and settled on core-to-core tunnels only over our WAN links and a standard of 4 tunnels per link. So that if we exceed the configured capacity of a WAN link, a quarter of our traffic swings at that point. The traffic follows our lowest metric topology unless there's congestion. It reacts within 15 minutes because of the auto bandwidth, and when the bandwidth recedes, we restore back to lowest metric topology within 15 minutes of clearing the challenge. So on the topic of monitoring, I had originally set up to do some monitoring and tools in a tutorial presentation, but found that this was more prevalent and what I thought was more contributory at this point. A couple of key monitoring tools, though. Consider what you can from a homegrown tool set to research many or all facets of your customers' configurations and consolidate that information for your help desk or NOC. That will in turn allow you to minimize the need to share your enable passwords and allow them to get a lot of status from simplified tools. For us, two biggest things were MRTG with some homebrew enhancements and syslog. So our MRTG, which I'll show you in a moment, has a simple link for each port to a cutesy, but it works, network diagram, a link to telnet to the CPE, and a quickie document on most of our smaller links on how to configure that CPE if it's our standard brand. We've also gone with a syslog implementation that has a Perl wrapper that does some basic color coding for up and down, so our relatively inexperienced NOC staff can get a sense of what's going on just by looking at the colors. Also substitutes in the interface description so the entry has a local meaning. We felt that the syslog was quicker for us to make useful because the syslog message has all the text you need to decode what kind of message it's trying to tell us, whereas the SNMP would require a lot of translation and might potentially have a lot of excess messages. So on the security, just to preach the standard song, please prevent your bad traffic, do your anti-spoofing, unicast RPF unless you can't. We also use a very simple but a very effective inbound ACL on every port leaving our core or our production network. If it's facing a provider, if it's facing a partner, if it's facing a customer, there's an inbound access list that we update as we see fit. Black hole routing has saved our butt. Being able to dump away a DOS attack helps mitigate the impact on many other vulnerable customers at the same time. And we've got just enough net flow in place to be able to help us track down source and destination of that DOS. Typically, our approach is to black hole the victim initially until we can go back and cull the data a little bit better and figure out if it's truly distributed, in which case there's not much that we felt we could do, or if it's coming from a few key attack points, in which case we'll black hole the source of the problem and unblack hole the victim, allowing them to mostly resume business and service and move forward from there. So that's my story. It's worked well for us over the 5 years. Technically, I'm on call 24/7, even on vacation and whatnot, but my phone rings about once every 3 months, and I attribute a lot of that to what we've talked about here this afternoon. If you'd like configuration snippets from any portion or all portions of this program, feel free to track me down by email. Be happy to show you what we use and so forth. And a couple of samples real quick. Here's our syslog implementation. We've color-coded down as red, cleared as green, up as green, same for BGP neighbors. Also translated this POS interface to being an OC3 to a partner of ours. And then as well, here's a look into our MRTG. This particular dist router has our T1 customers. I've temporarily renamed one of our customer ports to be unnamed. So here we've got a way to look at the network diagram. This is actually generated from rancid configs, but it just sucks in a JPEG of a 7507, sucks in it. What? Yeah, all right. I forgot this only gets generated once a day for the diagrams. Culling through the rancid stuff was a little bit slower, but gives us the link subnet from our distribution router to the CPE, the network and the far side address. It tells us what kind of interface it is, what router card assignment, T1 assignment, time slots, and then on the bottom side shows the LAN network, what the subnet is. For the many NOC employees we have who don't understand slash notations, gives them a quick slash conversion table with a bunch of notes at the bottom that are relative to our implementation. A quickie on administrative distance if needed, and rarely gets used there, and a little bit on internal tags. Our classic CPE was AdTran, so this walks them through the menu-based structure step by step to configure it, gives them a quickie link to Telnet to it if they should so desire, and some SNMP correlation, or actually it's, I think it is SNMP to pull it, and gives us a link status and then allows us to go into the last 24-hour counters for every 15 minutes. So at this point, it's 25 minutes to beer and gear, which means we've got about 25 minutes for questions, or if there's anything else you'd like me to elaborate on, dive in further and show. Any questions? All righty. As mentioned, feel free to contact me if you'd like any glimpse into configurations, and orbit a bit, and we'll be down at Beer and Gear.